All right, welcome back to section 5.7. We are going to finish up talking about the fundamental theorem of algebra and add a new idea to analyzing a polynomial's roots using what's called Descartes' rule of signs. Yesterday, or I should say in the other video we looked at the total number of zeros in a polynomial called the complex zeros, and then split that up into real and imaginary just by understanding that imaginary come in pairs. So we started at the highest even number that we could and then went down by 2 until we got to 0. So if we had a quintic polynomial, for example, degree 5, then we would actually have either 4, 2, or 0 possible imaginary zeros. What we're going to do now is break down those real zeros into whether they're positive or negative. By looking at the sign changes in a function, we can count how many positive zeros there are. So in this example, 4, which is a quartic polynomial, total of 4 complex zeros. In fact, I'm going to put that down in my first scenario here. Notice that our table is a little bit more complicated looking because now the real are split into both positive and imaginary. But we're going to treat it the same way we did on the other table, where we have these possible scenarios. Right now I know I have 4 complex, so I just have this one scenario going on right now. Let's find out how many positive there are by counting the sign changes. Here's one sign change, because we went from positive to negative. There's another sign change, there's another sign change, and there's a fourth sign change. So there's 1, 2, 3, 4 sign changes. 4 total sign changes. I don't know why I have the word total there. 4 sign changes. Means that at most there are 4 positive real zeros. There also could be 2 or 0. So we went down by 2. It's kind of like we did with the imaginary yesterday, and it's related to the fact that the imaginaries come in pairs, because that'll work out with in the end when we put the imaginary in. So we know that the positives can have either 4, 2, or 0. There could be 4, 2, or 0 positive real zeros. So I know I'm going to have 3 scenarios. Okay, possibly more, depending on what the negatives give us here. So here's how we find the number of negative zeros. We put negative x into the function. So I'm going to have 2 negative x to the 4th minus 8 negative x cubed plus 6 times negative x squared minus 3 times negative x plus 1. We simplify this function. Now remember, when we take a negative value to an even exponent, it will become positive. But a negative value to an odd exponent is negative. So let's look at this here. Negative x to the 4th is going to be x to the 4th. So we have 2x to the 4th. Negative x cubed is negative x cubed. Times negative 8 is positive 8x cubed. Negative x squared times 6 would just be plus 6x squared. Negative 3 times negative x is positive 3x. And then we have plus 1. Okay, and now what we do is we count the number of sign changes here. Well, we have all positive values here, so there's 0 sign changes. So 0 sign changes means that, let's do this here real quick. 0 sign changes means that we have no imaginary no negative zeros. Not sure why this isn't changing colors. Oh, this is why. You know how I'm picky about my colors. There we go. That's blue, so we're going to make this one blue too, and then I'm going to make the negatives red. Alright, so we have 0 sign changes, or no sign changes, which means that there are 0 negative real zeros. Okay, so all we have in these scenarios are 0, negative, real zeros. So to find the imaginary, obviously, they have to, all our columns have to add up to that number of complex, which is 4 in each case. So we know 4, 4, 4. We know that the imaginary then are going to be 0 because all 4 of them are positive real. Here we're going to have 2 imaginary because 2 of them are positive real. And here we are going to have, oh, what did I do there? And here we are going to have 4 imaginary because none of them are positive and none of them are negative real zeros. So the reason why we had to go down by 2's here after we found out that there were 4 sign changes, okay, once we get that 4, the reason why we went down to 2 and 0 is because that helps solidify the fact that there are going to be an even number of imaginary zeros since they come in pairs. Before we move on to the next example, I just want to point something out here that's going to make things go a little bit faster. In order to come up with this f of negative x function a little bit more quickly, notice that the only terms that changed signs had odd exponents. Okay, 3 and the 1. That went from a negative to a positive, and this one went from a negative to a positive as well. All the even degree terms stayed the sign that they were, and it doesn't matter if they're positive or negative to begin with, they'll be that same sign in the second function, f of negative x. So we're going to use that in this next one. Okay, but first we're going to count our sign changes. So we've got, let's see, 1, 2, 3 sign changes. So that means that we either have 3 positive real or 1. Let's just say 3 or 1 positive real zeros. 3 or 1. So far we have 2 possible scenarios. So I'm going to come down here. We had a quintic polynomial to start off with, degree 5. So I'm going to come down here and I'm going to put that in both these cases, we know the total complex zeros is 5. And I'll take a look at the f of negative x function. Now remember, the only terms that are going to change signs are these odd degree terms. Okay, so the x cubed, the x to the 5th, and the negative x to the 5th. Those are the 3 terms that are going to change signs. So what we're going to have is 3x to the 5th minus 4x to the 4th minus 2x cubed plus 5x plus 12. We don't need to worry about the fact that there's no quadratic term here. That doesn't affect the counting of the sign changes. So let's count some sign changes here. We've got a positive to a negative to a positive. So we have 1 or 2. I'm sorry, we have 1 and 2 sign changes, which means we have 2 or 0 negative real zeros. So in our table, now this is what's going to be interesting here, is that the 2 or 0 can go with the 3 and the 1. So first I'm going to put the 2 and the 0 with the 3 and the 1 like that, but now we can also say, well, I could have the 3 positive together with 0 negative. And I could have, I'm going to have to add in another column here, fourth scenario, scenario number 4. Just extend these here. I could have the 1 positive matched with the 2 negative real zeros. And now I just need to find out, so I'm going to need some more 5s in here. I just need to find out how many imaginary they are because they have to total 5. Well, here I have all 5 being real zeros. 3 of them positive, 3 of them negative. Here I have 1 of them being a real 0, a positive 0, so that means 4 are imaginary. Here 2 of them would be imaginary, and here 2 of them would also be imaginary. Okay, but in these cases where we have 2 imaginary, in our table from just using the fundamental theorem of algebra, these would have been covered in the same scenario, because we would have said, oh, there's 3 real and 2 imaginary. But now we broke down how many real there are by the number of positive and negative possible pairs there. So we have 4 scenarios that could happen in that case. Okay, we have one last type of problem to do here, and it is finding all the zeros of a function. Okay, we're not given any information. So what we're going to do is list out the possible rational using the PQ test. And then in order to just speed things up a little bit, we're going to graph it and get a 0 from the graph. So let's find the P over Q's first. Remember, P is the factors of 14, Q are the factors of 1, so these are just going to be the same as the factors of P. So positive, negative 1, positive, negative 2, 7, and 14, all the factors of that constant. So if there are any rational zeros, they're in that list right there. Let's go find out if there are any. We'll go to our graphing calculator. I've got part of it plugged in. Actually, this is the second time I've done this video, because the first time I did this video, I had the screen zoomed like this, no lie, and I thought that was the end of the function, and I graphed that graph and could not figure out why my 0 was not working in synthetic division. So that's why I'm doing this video. So we're going to continue on with the rest of that function the way it's supposed to be. 10x squared x. Oh, come on. There we go. 10x squared minus 13x and minus 14. Okay, I'm going to go to the graph. And I just have it at the standard zoom, so if you're getting any sort of error here, make sure your plots are off, or if you can't see anything, we may have to change your window. Okay, we're going to do a sketch of this too. Anytime you use a graph to help you out for anything, okay, not just these problems, but for anything, anytime you use a graph, we want you to make sure that you do a sketch. All right. It looks like our function is tangent at -1, goes back down, so it's going to do something like that, goes back down through -14, and then appears to go back up through 2, okay? That's what it looks like. Okay, something might be different there, but we'll find out. -1. All right, so let's try that -1 in synthetic division first. If you want to do the 2 instead, you can. But we've got 1, -4, 4, 10, -13, and -14 as our coefficients. So we're going to drop this, multiply, add them up, multiply, add them. Continue on with our synthetic division here. This looks good. Okay, now here's the problem. This is a coefficient on x to the 4th, since this was a coefficient on x to the 5th. And we don't know how to factor this, so what we need to do is continue on with some more synthetic division. Well, we've got a 2 there, but now think about this. If we do synthetic division with that 2, we're going to drop this quartic down to a cubic, and unless if it's factorable, there's nothing that we're going to be able to do. Sorry, my wife is dancing in the living room here trying to get me to laugh, but I refuse to do so. So as we continue on here, we might need to use a third 0. I only have 2 listed here, so think about what we would need to do. We'd have to recognize that this is a multiplicity of 2. Okay, I'm sure as you graphed it, you probably even thought that. So if you want, you can actually just do -1 again, because it's it counts as a second 0. So we drop the 1. Let's see here, something, maybe that's not right somewhere here. 1. Oh, I guess she got to me. There we go, 15, -15, -14, 14, and 0. I don't think that's groupable. So it's a good thing we recognize that that -1 had a multiplicity of 2, so that we could do synthetic division with 3 zeros total and get this thing down to a quadratic. So we'll drop this. All right, so we have a quadratic here now. So remember, the rule is even if I had more zeros on the graph, it doesn't matter. We have to stop at a quadratic and solve. So here we are. I'm going to list all my zeros here we have negative 1 with a multiplicity of 2. This is not going to be nearly enough room. So I'm going to move this. And then as I find more zeros, I'm going to just write them here as well. We have 2. And then we're probably going to get 2 imaginary because we don't see it crossing the axis anywhere else, which it couldn't because it's a cubic, or excuse me, a quintic. Actually, it could be crossing that. Maybe outside of our window, it's actually going up and coming back down and going through again, because that would add up to 5 zeros, and would follow along with the end behavior that it's supposed to have. But I don't think it does that. So let's go ahead and solve this here. Looks like completing the square is going to be pretty easy because of the even b term. Add 4 to both sides, complete that square, which means we now have negative 3. So we are going to get an imaginary because we're going to take the square root of both sides and have x equals, let's take this one step at a time here. X minus 2 equals positive or negative. There's your conjugate pairs. I square roots of 3. Excuse me, irrational conjugates. Not complex conjugates, but irrational here. Oh no, I'm sorry, it is complex because of the I. Now we're going to add that 2 over. There are your imaginary answers. 2 plus I square roots of 3 and 2 minus I square roots of 3. So we have 1, 2, 3, 4, 5 zeros because of the multiplicity of 2. We can count it as 2. So we have 2, 3, 4, 5 zeros of that function. All done.